So, as data scientists, a lot of times we deal with imperfect data. The data that we have is kind of what we have to work with, and we don't have the luxury of having perfect data to build our models. And one type of imperfect data that's pretty common is unbalanced data. And I see this a lot in the industrial space when I do equipment failure. Typically, machines are designed to last a long time, and it's not uncommon for a machine to run very efficiently for years, maybe 3 years before it fails. So when you look at that and you try to predict that failure, a lot of times you will have literally 3 years of non-failure data before you get that one failure. In recent years, I've seen a real strong trend towards balancing the data. And by balancing, I mean using some kind of technique to change your data so that it's more on a 50-50. So instead of having one failure in every 100, you have one failure out of every two. So balancing your data, creating a more 50-50 split. And, there's certainly nothing wrong with that. In fact, very recently I worked on a POC where I balanced my data using a SMOTE algorithm, and it worked beautifully. It was amazing. It did a great job, or it turned out really well. But it's important to understand what you're doing to your data when you balance it. Namely, you're not affecting the averages or the standard deviations very much, but you are having a tremendous impact on the standard errors of your parameters that you estimate. And those parameters can be parametric or non-parametric. And parametric would be something you would estimate in a regression. Non-parametric would be something that you would estimate in a decision tree most of the time. Something like a shade tree, a chi-square test. Anything based on a chi-square is would be affected, as well as a t-test, which I'll show in this video, which is a parametric procedure. So, in this video I walk through. I start with a data set and I balance it using three different techniques, and I show how that balancing actually impacts the hypothesis test and the parameter estimates. So, anyway, thank you very much. All right, so first let's take a look at our data and just kind of see what we're dealing with. Pretty simple data set. It's equipment failure. We have 5 different fields in this table I'm reading in. We have the date, the machine ID, the equipment failure, the age of the equipment, and the location of the plant. So, for example, this particular machine on September 13th, 2016 did not fail. If it was a 1, it would have failed. Here it's 0, so it did not fail. This is how old it was, 457 days on this particular date, and it's located in Dallas. And there's 2 different places that a machine can be located in this data set. One would be Dallas and one would be Houston. In terms of the number of records and all that kind of stuff, we have 451,000 records. 617 of those are failures. So our failure rate is really, really small. It's less than 0.1%. So that's, given the small failure rate, would be a reason why you'd want to use some kind of rebalancing technique. And we'll be looking at 3 different balancing techniques. The first is called upsampling. It first would be upsampling your failures, or sometimes it's called boosting. And what you're doing with boosting really is you're just double counting your failures, right? So, if we have, right now we have 617 failures. If we double counted every single one of them, our failure rate would go from 0.1% to 0.2%. I mean, it would double, right? So you're just doubling your failures. But it's one way you can balance your data, by just double counting, your failures. Another way that you can balance your data is to downsample your non-failure. So, if you took a 10% random sample of these 450,000 records, you wouldn't have 450,000 non-failures. You would have roughly 45,000 non-failures. So it's just a way to get your failure rate higher, or to balance your data. The third way we'll be looking at is SMOTE, and it's a little bit more complicated. With SMOTE, you're synthetically generating new failures. So you're not double counting your existing failures, you're synthetically generating new ones. So I won't get into all the details of how SMOTE works, but it's a relatively new technique, but it's how you would, it's another way that you could balance your records. The thing I would point out, and I want to be very clear about this, is that we're not fixing the problem, really, because I hear all the time, yeah, I had an unbalanced sample, so I fixed it with SMOTE. Well, you're really not fixing it. I mean, you're making the best of what you have. Like if you have 12 failures, here we have 617, but let's say we had 12 and we use SMOTE to increase it from 12 to 50,000. I mean, those new records, we're not creating those out of thin air. We're not creating this alternative universe where we're generating more failures that are truly different than the failures we have. Um, we're just taking our existing failures and we're creating representative samples of those failures. So it's, in a sense, it's making the best of what you have. It's really not fixing the problem. And this is true with inferential statistics, but it's especially true when you have a small number of records. If you have 12 records, and you can build a great model on those 12 records, but if the 13th failure comes along and it's materially different than the previous 12, your model's not going to predict it. I mean, bottom line, it doesn't matter if you smote those 12 records, you're still not going to predict that 13th because it's materially different than the previous 12. And that's true with pretty much any model you build, but when you only have 12 records or you have a limited number of records, it's a much bigger issue. I mean, if you have, 12 million failures, the 12 millionth and first, if it's different than the previous 12 million, you're not going to predict it. But chances are, if you have 12 million records, there's a lot better chance with 12 million records that the 12 millionth and first will be more like the 12 million than if you have 12, then the 13th would be like the 12, if that makes sense. So with SMOTE, like I said, you're not really fixing the problem, but you're mitigating the problem. All right, so let's look at the simple statistics. And we're going to look at the average value of tenure or age of the equipment for our failures. All right, so here we have the average age of failures for the original data, for the downsampling of the non-failures, for the upsampling of the failures, and for SMOTE. All right, so originally we had 617 failures. The average age of a failure is 508. The standard deviation of a failure was 200. When we downsampled the non-failures, or when we bagged the data, we still have 617 failures, so we didn't change the failures using this technique, so we didn't really change the underlying statistics, right? They're the same. When we upsampled the failures, again, we don't change the mean and the standard deviation, but we substantially changed the number of records, right? Because we double counted a bunch of records. So the mean and standard deviation don't change, but the number of records change. Something else that changes is the standard error of the mean. So here the standard error of the mean is, and this is going to be critically important when you're doing parametric statistics like regression, or even if you're doing like chi-squared or non-parametric statistics. You increase the number of records, you're going to dramatically increase the statistical validity of your hypothesis test. So here the standard error mean was 8.052. And here it's an order of magnitude lower. Same thing up here with the SMOTE algorithm. We're dramatically decreasing the standard error of the mean. So these balancing techniques, they don't, downsampling non-failures or bagging doesn't affect your standard error. None of the techniques affect your mean or your standard deviation, but SMOTE and boosting are going to dramatically have an impact on your standard error of the mean. And let me show you what that translates into. We're going to look at some simple t-tests. All right, so here's the original data, and where's the original data right here? So we're going to see if there's a significant difference between the average age of a failure between Houston and Dallas. And in Dallas, the average age of equipment when it fails is 513 days. In Houston, it's 504. Doing a simple t-test on the data, this is not a significant difference. Likewise, with the bagging technique or the downsampling of the non-failures, it's not significant. This difference is not significant. However, when you boost the number of records in your data set or the number of failures in your data set, these t-statistics become significant. So it's the same difference here, right? 513, 513, 504, 504. But the hypothesis test becomes significant simply because we increase the number of records. With SMOTE, the averages change a little bit, but again, we're getting better statistic or better statistical significance in our hypothesis test. And you would get, if you were going to build a regression model, you would be much more likely to find statistically relevant variables when you upsample or when you boost or do smoke than if you did it on the original data. So again, I'm not saying this is a good thing, it's a bad thing. Sometimes I use it, sometimes I don't, but I think I've heard so many people talk about how it's like a cookbook thing. You take your data, if it's not balanced, you balance it. But everybody needs to understand that there's consequences of that, and that your model is going to look very different, or can look very different if you've got a balanced data. If you use one of these techniques to balance your data before you actually build your model, than if you just build a model on the irregular data itself. Anyway, hopefully that's helpful. Thanks a lot for your time.